Every second, thousands of cosmic rays, mostly hydrogen and helium nuclei, strike every square meter of the Earth's upper atmosphere. We don't really know where they come from, but we do know that when cosmic rays crash into air molecules in the atmosphere, they create a shower of other fundamental particles. Pions, kaons, positrons, electrons, neutrons, neutrinos, gamma and X-rays, and muons. We know this because we have particle detectors in labs down on the surface that detect the directions and energies of the particles in these showers, and use them to study the original cosmic rays. But there's something fascinating about the fact that we detect a lot of the muons from cosmic rays down on the surface of the Earth. Because muons, if you make them in a laboratory, only have a 1.5 microsecond half-life before they spontaneously decay into an electron or positron and some neutrinos. And yeah, the Greek symbol mu is used for both muon and for microsecond, which can certainly be a little confusing. But the lifetime of muons is really close to a microsecond, so it's also kind of beautifully appropriate. Anyway, the point is that if you have a bunch of muons, you'll only be left with about 50% after 1.5 microseconds, and 25% after 3 microseconds. And after 10 microseconds, there will only be 0.1% of the muons left. Muons don't live very long, just 2.2 microseconds on average. To put that time into perspective, light travels fast enough that in 1 second it could go around the Earth 7 times, but in 2.2 microseconds, light will only travel 660 meters, or less than half a mile. So even muons traveling at essentially the speed of light wouldn't make it more than a kilometer or two before the vast majority of them decayed, which is far less than the 10 or 20 or 30 kilometers that muons do regularly travel from the upper atmosphere to the ground. So how do muons travel dozens of kilometers through the atmosphere without spontaneously decaying, when in fact they should only be able to travel less than 1 kilometer? Time dilation. Yes, because the muons are traveling close to the speed of light, their time literally passes more slowly. At a speed of 99.5% the speed of light, 2.2 microseconds for them would be about 22 microseconds for us, enough time for the average muon to travel at least 6 kilometers before decaying, instead of half a kilometer. And even higher energy muons going even faster would even more easily reach our detectors on the Earth's surface before they decayed. At 99.995% the speed of light, the average muon would live for 220 microseconds and travel at least 66 kilometers before decaying. So from our perspective, the fact that so many cosmic ray muons reach our detectors on the Earth's surface is direct evidence for special relativity and time dilation. But what about from the muons' perspective, where they do only live on average 2.2 microseconds? Well, for them, the answer to the apparent paradox is also relativistic length contraction. From the muons' perspective, it's the Earth and the atmosphere which are moving, at 99.995% the speed of light, towards the muon, and the lengths of moving objects are literally contracted by a factor dependent on their speed. In this case, 50 kilometers of our atmosphere is, to the muon, literally only half a kilometer, which is thin enough for even a muon with a lifetime of 2.2 microseconds to traverse. Well, actually, from this perspective, the atmosphere and ground move past the muon, but at a speed of 300 meters per microsecond and a distance of only 500 meters, the ground has no problem reaching the muon before the muon decays. This, in my mind, is one of the most awesome experimental verifications of special relativity. The unequivocal time dilation, or length contraction depending on your perspective, for objects moving close to the speed of light. They literally couldn't get here if it weren't for time dilation. The specific time dilation and length contraction factors I talked about can be calculated using the time dilation and length contraction formulas. Once you know how to use them, you can plug in any speed you want and see how much distances and time intervals will be distorted. And Brilliant.org, this video's sponsor, is a great place to learn about not just the details of time dilation and length contraction, but many of the other amazing equations that describe our universe. Like, they have a course that leads you towards understanding the Schrödinger equation of quantum mechanics, and one on Hubble's law in astronomy, and the famous Bayes' theorem of probability and statistics. And the first 200 people who go to Brilliant.org/minutephysics will get 20% off a premium subscription to Brilliant with access to all of Brilliant's courses and puzzles. Again, that's Brilliant.org/minutephysics for a deeper understanding of the equations, and not just the concepts, that underlie our universe.